you for that introduction, Professor Carl. The paper I'll be presenting today applies the Deformable Organisms framework to the problem of skull stripping. This is joint work with Professors Joshi, Thompson, Toga, Shattuck, and Terzopoulos at the Laboratory of Neuroimaging, UCLA. I'll describe what skull stripping is, some of the existing automated algorithms that perform skull stripping. Then I'll go into details of our Deformable Organisms method, describe how we evaluate it with the widely used automated methods, interpret our results, and then discuss future work and implications of the method. I'll start with describing what skull stripping is, where it's used, and how it's traditionally done. Skull stripping is delineating the brain in whole head magnetic resonance images of the head. It separates the brain from the skull, skin, eyes, neck, and cerebrospinal fluid that surrounds the brain. It's used in registration, in longitudinal studies, in understanding how the brain is affected by disease, and extracting a cortical surface. Traditionally, it's done by experts who are trained in anatomy, who go in these volumetric images slice by slice and trace out the boundary of the brain. But this can be a time-consuming process and may not be consistent across tracers. Now I'll describe the existing approaches. Many of them, the widely used methods, are popular because they're part of existing neuroimaging toolkits. And then I'll discuss meta-algorithms that combine existing methods to produce a better result. The brain surface extractor is part of the brain suit set of tools and applies edge detection to the subject T1 magnetic resonance image. It does this to produce a connected component that roughly delineates where the brain is. It then applies morphological operations to this connected component to separate it from extraneous material in the head. But may run into issues if there's a strong connection between, say, the eyes and the brain. The brain extraction tool is part of FSL and deforms a deformable mesh to find the boundary of the brain by looking at the local intensities in the image. But it may run into problems because it doesn't incorporate global tissue classification or any kind of global knowledge in the image. The hybrid watershed algorithm applies the watershed transform to the subject image to get a rough idea of where the brain is, and then it fits it to a deformable template model. It deforms that model more to refine the segmentation, and it's part of the free surfer set of tools. Rex et al. Produced a meta-algorithm in 2004, and what they do is they learn how to combine multiple automated approaches by comparing their results to manual tracings. And they learn a way to look at every single voxel location and combine the results effectively to create a better segmentation. The multi-atlas propagation and segmentation algorithm uses multiple atlases on the fly to create a segmentation of the brain. Many of these algorithms are currently being used in neuroscience studies, but they require manual intervention and cleanup, which highlights the point that we need better skull stripping algorithms so that we can create more accurate segmentations and don't require any manual intervention. Deformable organisms provide high-level control mechanisms by borrowing ideas from the field of artificial life. They combine sensing, reactive behavior, proactive planning, and knowledge representation to create a high-level plan so that the organisms can cooperatively segment an image. Our organisms framework combines multiple image processing of our original T1 magnetic resonance imaging. We use 3 different processings. A threshold of the image, we do this by taking the intensities in the original T1, fitting them to a histogram, and finding the point that separates the voxels located in the head from those in the surrounding air and noise. We also do a k-means classification using 2 and 3 means, The slide depicts a 3 means classification, and what this does is give us a very rough idea of the tissue composition of the brain. And finally, we do the gradient, and this gives us information about the edges in the image. Our deformable organisms are separated into layers. The high-level layers use the information and knowledge provided by lower ones to accomplish different goals and objectives in the image and create a plan to segment. They're defined into 5 different layers. Each of our organisms is represented as a 3D triangular mesh. They start as a sphere, and we iteratively deform them to model whatever region we decide the organism should find. At every iteration, we apply Laplacian smoothing to constrain the way the mesh deforms. For example, we don't want the meshes to intersect with themselves, and Laplacian smoothing will prevent this. Our organisms are embedded in the image space. Because of this, we can sample at the vertices of the mesh using nearest neighbor interpolation from the original T1 magnetic resonance image, the gradient image, the 2 or 3 means classification, or our threshold image. The motor control layer dictates how we allow the mesh to deform. In our case, we let the vertices move along the lines normal at the vertex with respect to the mesh's surface. We sample intensities along this line, shown in yellow, from whatever image it's embedded, and this is how we sense the images. This figure right here shows the corresponding intensities from that line. In this particular case, this is from the original T1 image. It starts with the air outside the brain, the spike is the skull and skin, and then it goes into the brain matter. Our behavior layer is where we specify how we analyze the intensities along the normal lines at every vertex in the mesh. It can be designed so that the organism is attracted to certain features or landmarks in the image, or it can use that information to understand where it is located with relation to all the other organisms. The cognition layer combines behaviors to create a plan for segmentation. This plan right here is the one we created for skull stripping. The left part uses the 4 different processing of our original T1 magnetic resonance image, and the right shows 4 organisms, 2 for the eyes, 1 for the skin, and 1 for the brain. Each organism has specific objectives that they need to accomplish, and others build on that information gained to cooperatively segment the brain. One important thing to note here is that you can design your plan to account for difficulties and problems in the image. For example, if your eyes are cropped out and the eye organism is unsuccessful in finding a boundary, you can account for that in your plan, and other organisms can rely on different parts of the image to complete their tasks. I'll now describe the skull stripping plan we developed in detail. We begin by initializing our skin organism as a sphere. It senses the threshold of our original T1 magnetic resonance image and deforms to find the boundary of the head. We then analyze this boundary to locate the nose, and then from there the 2 eyes. At these eye locations, we initialize 2 eye organisms that sense our 2 means classification to deform and find the boundaries of the eyeballs. We then deform our skin mesh a second time into the head, through the skin and skull into the cerebrospinal fluid that surrounds the brain. And then we deform our eyes a second time by sensing the 3 means classification of the image. This lets them encompass the tissues that surround the eyes. And then from the locations of the skin organisms and the eye organisms, we're able to initialize a brain organism. And this deforms itself by sensing the 3 means classification and the gradient of the original subject image. it's constrained in its deformation by the locations of the skin organism and the eye organisms, meaning it won't be able to deform into areas, for example, where the eye is already occupying. We use a 3D rasterization algorithm to convert the brain mesh into a binary volume and thus complete our segmentation. Now I'll describe how we evaluate our method with 3 of the widely used algorithms: brain surface extractor, the brain extraction tool, and the hybrid watershed algorithm. We use the segmentation validation engine, which is an online tool that allows users to download 40 images from the Loney Probabilistic Brain Atlas. You segment them using whatever algorithm you choose and upload the results. The online tool will compare your results to manual tracings of those images. We use the manual tracings as a gold standard. It uses 4 overlap metrics and error projection maps to quantify how your automated results differ from the manual segmentations. This allows you to compare your method with algorithms all over the world. I'll now describe the results that we found comparing our method to the 3 approaches with the overlap metrics and the error projection maps. The table at the top shows the average overlap metrics across the 40 images from the Loney Probabilistic Atlas with respect to the 4 methods we compared. We then did paired sample t-tests on the individual results across the 40 brains and found that there's no significant difference in the deformable organisms method compared with the brain surface extractor and brain extraction tool for the sensitivity and specificity measures. We also found that there's no significant difference in the performance of brain surface extractor and the brain extraction tool. The average false positive error projection maps give you a visual idea of where your algorithm includes too many voxels in the boundary of its segmentation. That's shown in the first column. It shows that the deformable organisms method includes too many voxels in the inferior and anterior parts of the occipital lobe and too many in the temporal lobe. The brain surface extractor and brain extraction tool keep too many voxels in the posterior part of the occipital lobe. And the hybrid watershed algorithm includes too many voxels throughout the boundary of the brain. Because of this, it has a very small average false negative error shown in the second column. And what that does is it captures where your algorithm crops out too many voxels. Our deformable organisms method did do a good job at delineating the medial longitudinal fissure, which is the groove that separates the 2 brains. I'll now discuss future work and implications of this framework. Our deformable organisms provide an advantage when you're working with difficult or problematic data. If you have blurry images, parts of them are missing, you can customize your organisms to deal with that. And it provides extensive room for expansion. You can create a plan specific to your set of data. Organisms that look for features specific and that are only included in your data. If you have tumors in your data, you can have an organism specifically look for those boundaries, and other organisms can use that information to help with their own tasks. And this framework is generalizable to any type of medical imaging task or any type of segmentation task in general. Thank you for your attention, and please ask any questions you may have.
Yeah, I guess I have a kind of a very general question. Maybe you can give me some insight here. So in the medical imaging literature for something like 20 years now, there's been a framework of deformable atlases, and which is basically a well-understood deformable organism model where every structure is an organism. Whatever you want to call it, basically, it's something that captures the relationships between different brain structures. And there are formal ways of regularizing this, of having data driving terms, using different features, and so forth. So I wonder, this new framework, where exactly where does it stand in relationship to this literature? Because it sounds like basically it's a set of regions that inform each other and simultaneously warp, segment different.
Yeah, I mean, that's a good general question, Professor Davids. What it does is it allows you to incorporate this very high-level understanding of whatever task you're trying to segment into your algorithm. So, I mean, in our case, we parameterize our organisms for three different areas in the brain, just for segmenting the brain. But all it's trying to do is provide a framework for you to just directly create a simple plan to segment an image. Instead of using edge detection or some kind of low-level algorithm and then tweaking it to segment a brain, this is just trying to come up with just a few lines of code or specifications so that you can segment something and have all the rest automatically done by these organisms that you create. So, I mean, you can create an organism that is generalizable for a specific task in multiple type of medical imaging, and hopefully what that'll allow you to do is use a few simple rules to segment a complicated part of an image. And all it's trying to do is to create an environment where that's very simple to do.
Any other questions? Okay, thank you very much, and let's thank all the speakers.